Well, this is lecture 4 of basic calculus 1. So, in the last lecture, we had introduced the notion of function and then gave some examples. The examples were limited to so called algebraic functions, which means it is coming from the power function and then rational functions, polynomial functions and so on. So, today we will be discussing more examples. They will be including transcendental functions. Of course, that includes trigonometric functions, so which are not algebraic specially. And there will be something, say, once we discuss trigonometric functions, we will also discuss inverse of trigonometric functions. So, the notion of inverse of a function also will be introduced. And then we will discuss some properties like increasing nature or decreasing nature of functions and so on. So, let us start with our examples. So, first we will consider the exponential function, which is given as f of x equal to a to the power x for some positive a, fixed positive a. So, recall that when you take the power function, it is of the form x to the power a, where a is fixed and x is the variable. Now, this is in the form a to the power x, where a is fixed and x is a variable. And of course, we will assume that this a is not equal to 1, because you will get the constant function otherwise. So, these are called the exponential functions, which are in the form a to the power x. Now, if you take a to the power x, here x can vary over the whole of set of real numbers. So, that is, we will write its domain is minus infinity to infinity, it is the whole of R, and its codomain is positive reals. It can never be 0, of course. So, some examples are, say, y equal to 10 to the power x, where a equal to 10 here, and it looks something like this. When you take this yellow line, that gives y equal to 10 to the power x. And when you take, say, a equal to 3, you would get y equal to 3 to the power x, which is your magenta line. And when you take a equal to 2, y equal to 2 to the power x, that is shown in the blue one. And if you take its reciprocal, say 1 divided by a to the power x, that is, x now is replaced by minus x. So, say a equal to 10, you get y equal to 10 to the power minus x, which is on the second figure, the yellow one. Similarly, y equal to 3 to the power minus x gives your magenta one in the second figure, and y equal to 2 to the power minus x gives the blue one. So, that is how the curves look like when it is an exponential function. So, look at the nature here. When x decreases, it is going up and up in 10 to the power minus x. On the other side, when x increases, it is increasing, 10 to the power x is also increasing. Okay, we will come back to increasing and decreasing later. Now, let us take another, which is the inverse of this exponential function. So, that is, we will write that as log x. So, here y equal to log x to the base 2. So, what is the meaning of this to the base 2? It says that when you take a to the power log x to the base a to the power another function, which is our f of x here, log x to the base a, that will give you x. Similarly, when you take f of a to the power x, that is log to the base a to the power x, that also gives you x. That is how it is the inverse of a to the power x. So, their composition will give you the identity function, that is what it means. So, here you see that a to the power x log of a to the power x, this is our f function f, which is log to the base a. So, a to the power x is always positive. So, then this log, its domain should be positive reals. And of course, you get back any x from this, depending on how this is behaving, whether it is less than 1 or bigger than 1. If x is bigger than 1, you would get log of that to be bigger than 1, or to be positive, and when this x is less than 1, you get log of that to be less than 0 or negative. So, that is how it looks. Let us look at the yellow curve. So, that gives you log to the base 5. That is, if you take 5 to the power x instead of x, then you would get x. Similarly, everything has to be interpreted. So, the yellow one is really log to the base 10, and the black one, which is log to the base 5, and the magenta one is log to the base 3, and the blue one is log to the base 2. That is how the curve should look like. If you look from the y axis side, just rotate it 90 degrees. Say, think of y as the x axis, the horizontal one. Look at it from the y axis side, it would just look like your a to the power x curve. Okay. So, these are called the transcendental functions, they are not algebraic, and that includes exponential functions, that is a to the power x, logarithmic functions, they are inverse, and of course, trigonometric functions, which will come soon. Okay, let us take the trigonometric functions. As you know, we have these 6 trigonometric functions: cos x, sin x, tan x, secant x, cosecant x, and cot x. So, now cos x is, as you know, in a triangle. If you take this one as your x, this angle as your x, then cos x is this length base divided by the hypotenuse. So, this x is really measured in radians. So, that is a real number, unit is the radians now. So, with that cos x, you would get a curve like this if you plot it. So, that is from minus pi by 2 pi by 2, it goes like this from 0, and then it decreases pi by 2 to 3 pi by 2, again it goes to 2 pi, and so on. Similarly, sin x would give, say, 0 to pi will be looking like this, slightly looking like parabola, but not it is. And you see, it is not up to scales. In y axis we have a scale different, x axis is a scale different here. If you take both the scales are same, then it will be looking a flatter type, something like this. So, that is how y equal to sin x looks like. And if you take y equal to tan x, its graph will be, say, minus pi by 2 to pi by 2 will be looking this way, and the same thing is repeated everywhere. But at minus pi by 2, tan is not defined, and at pi by 2, tan is also not defined, because at those points exactly tan is equal to sin x divided by cos x becomes 0 at minus pi by 2 and pi by 2. So, these are not defined at these points minus pi by 2, pi by 2, 3 pi by 2, minus 3 pi by 2, and so on. So, in the form 2n plus 1 by 2 into pi, at those points tan is not defined. And you look at y equal to secant x or sec x. So, there you have again minus pi by 2, it is 1 divided by cos x. So, again it is not defined at minus pi by 2 and pi by 2 and so on, like tan, and it is repeating in a different way. So, this portion will be repeating here 3 pi by 2 to 5 pi by 2, and similarly, and here again there is a repetition. So, if you look at y equal to cosecant x or cosec x, there is a shift from secant x curve, that pi by 2 shift. So, you get this way, just like your sin and cos, there is a shift. Similarly, here it is a shift, just looking like secant x, but shifted one. Then y equal to cot x, which is 1 divided by tan x, they will not be defined wherever sin x becomes 0. So, you can see what happens at 0, sin is 0, at pi also sin is 0. So, at 0 and pi they are not defined, similarly 2 pi, minus pi, and so on. So, that is how cot x looks like. This is 1 divided by tan x. Look at the domains. So, cos x has the domain as the whole of real number, sin also has the whole of real number, but tan x, its domain is real numbers except plus minus pi by 2, plus minus 3 pi by 2, and so on. And similarly, if you take secant x, again because 1 by cos x, so except plus or minus pi by 2, plus or minus 3 pi by 2, and so on, everywhere else it is defined. And look at cosecant x, it is 1 divided by sin x. So, except at 0, plus or minus pi, plus or minus 2 pi, and so on, it is defined everywhere else. And y equal to cot x similarly is defined everywhere except multiples of pi. and look at their ranges. So, cos x is always lying between -1 to 1. This is your -1, this is 1, -1 to 1. So, its range is -1 to 1, and in fact, -1 and 1 are also achieved. So, it is closed interval -1 to 1, and its period is 2 pi. Every 2 pi the pattern is repeated. And in sin x you get the range as similarly -1 to 1, it is shifted, and your period is also 2 pi. Look at tan x, again its range is -infinity to infinity, that is every value is achieved, the whole of real numbers, and its period is pi. Similarly, if you look at secant x, its range is look at cos x, it is -1 to 1. So, here -1 to 1 is left, but -1 and 1 can be achieved because 1 divided by. So, it is y less than or equal to -1 and y greater than or equal to 1. So, that means the open interval -1 to 1 is excluded from R, that is what the range is, and period is of course 2 pi. Now, when you look at cosecant x, similarly the same range excluding -1 1 open interval, everything else is there, and in cot x the range will be whole of real numbers just like your tan x, and period is pi. So, this is how the trigonometric functions look like. Now, let us go to your this trigonometric functions really gives you something else where odd and even functions becomes important. Now, we will say that f x is a function f is even if f of minus x equal to f of x for each x in its domain. So, the domain is whole of real number, say in case of cos x. So, there what happens, f of minus x, that is cos of minus x equal to cos of x, that is why it is an even function. And we will say that the function is odd if f of minus x equal to minus of f of x, and you see that sin is satisfying that condition, that is sin of minus x equal to minus of sin x. So, sin is an odd function. Now, if you look at the power functions, algebraic functions which we discussed earlier, x to the power 2n when you take, n is an integer, that becomes an even function because x square is same thing as minus x square and to the power n. But if you take x to the power 2n plus 1, then one minus sign is remaining. So, x to the power 2n plus 1 becomes an odd function. Similarly, secant x will become even function, and all the other trigonometric functions are odd functions. We will also have some inequalities which you could have seen from the graphs itself, that sin x is always lying between minus of mod x to mod x for every x in its domain which is real number system. So, minus mod x is less than or equal to sin x is less than or equal to mod x, and of course, both sin x and cos x have range -1 1 closed interval. So, you get -1 less than or equal to sin x less than or equal to 1, and also -1 less than or equal to cos x less than or equal to 1 for whichever x you take. We have another inequality which also becomes very helpful, that is 1 minus cos x lies between 0 and mod x. It is always positive because cos x has to be less than or equal to 1. So, it cannot be negative, therefore, 0 less than or equal to this, and this of course needs something more which we will see later using which tools it has been derived, but okay, this will be useful. 1 minus cos x is less than or equal to mod x also. Then another inequality which is very helpful, which is sin x less than or equal to x less than or equal to tan x for all x in 0 to pi by 2, because tan x we are taking there, and if you take positive, so x is less than or equal to tan x. Otherwise, tan can become negative and the other inequality will hold. So, if x is not equal to 0, in fact, this sin x less than or equal to x, where equal to sign only happens when x equal to 0. If it is not 0, then sin x is always less than x for positive x. So, in general we would say sin x is less than mod x for any x. Now, the idea of look at the idea of the function. So, when you define a function, we say that for each element in the domain, there is a unique value on the codomain to which it associates. That is what f does. That means whenever A is equal to B, think of distinct things, but they has become equal. So, when A is equal to B, f of A has to be equal to f of B, which we also expressed in the other way, that f of A is not equal to f of B implies A is not equal to B. Such a function we will say that it is one to one if and only if the reverse condition is satisfied, that if A is not equal to B, then f A is not equal to f of B, which means two elements A and B, different elements, cannot be mapped to the same element on the other side. So, this kind of thing will never occur. Two elements A and B will never be mapped to the same element here. So, if A is not equal to B, then f of A is not equal to f of B, which when in applications it is usually the other side implication becomes more helpful, where you say f of A is equal to f of B implies A is equal to B. We may write like this, f of A equal to f of B implies A equal to B. So, this is the condition for one to one, f has becomes one to one if this condition is satisfied. And of course, f is onto if its range coincides with the codomain, that is every element in the codomain has been mapped. So, that is what range of f must be equal to B. And we also find many more functions from the old ones, as you have done from the power functions. We have taken the polynomials like f of x is a constant, say 1, f of x equal to x identity function. So, you have another function which is giving 1 plus x. Now, we are giving a notation for it. We will say that that is addition of two functions. So, if f is a function, g is a function from the same domain to the codomains also. Domain for f and domain of g should be same, codomains of course must be same. Then you say f plus g is another function which at x takes the value f of x plus g of x. Though it looks very trivial, but it has to be read that way, that f plus g is a new function whose value at x is equal to the old value of f at x plus the old value of g at x. So, that gives you the value of f plus g at x. That is how we define f plus g. And when you take f minus g, it is again the minus sign on the other side. Similarly, you can have another function which is f times g, f g let us say. So, f g of x equal to f x into g x. So, like x is a function, f of x equal to x identity function. You take another copy, say f of x equal to x, then f into f becomes x square. That is an example of this. We can define also their division, say f by g at x will be f x by g x provided g x is not equal to 0, because we have to take care of division by 0. So, there is another way of doing this which is called the composition, that is f is a function, g is also a function. Then from starting from x, we can first go to f of x, then g acts here. So, that takes to g of f of x. So, that is how the composition looks like. First f acts, next g acts. So, this is written as g o f, because when you come to g of f of x, we preserve this notation, say that it is g o f, not f o g. So, g o f of x, g o f is a new function equal to g of f of x. But this needs some condition to be satisfied, because x goes to f x and this value f of x must be in the domain of g, so that g can carry it to the value g of f of x. So, that means the range of f should be contained in the domain of g, then only you can define this. So, we say provided range of f is a subset of domain of g. So, your inverse function will come from this composition. So, how is it coming? You take a function, say g, such that g o f equal to the identity function and f o g also should be the identity function. f of g will be defined the other way. First g would work, then f would work. So, in that case, if that happens, that g of f equal to f of g equal to the identity function, we would say that g is the inverse of f. So, in that case, it is required that f has to be 1 1, f has to be on 2, because if you go from f to f of x, then g acts here, it takes, but it becomes the identity function, these two are same. So, when you come back from the other side, that should be defined as a function. So, if it is not, f is not 1 to 1, there are 2 points to which it goes and g then acts, and that becomes identity. So, identity means this and this has to be identified. Similarly, this and this has to be identified. So, that means this, all these three are same. So, that is, it has to be 1 to 1. Similarly, on 2 also will come. So, that means f inverse will be defined provided f is both 1 to 1 and on 2. So, if f is a function from a to b, then f inverse has to be defined from b to a. It is 1 1 on 2. So, you just read the reverse arrows, then it brings you back to the same x. So, we say that f inverse y equal to x if and only if y equal to f x. That is the definition of f inverse. But this can only be defined whenever f is both 1 1 and on 2. So, once f is 1 1 on 2, f inverse also becomes 1 1 and on 2. So, inverse function will be defined only for those functions, and their inverses are also of similar type. So, that f becomes the inverse of f inverse. So, this is the way we had seen that logarithm and the exponential was working, a to the power x and log to the base a. It is this composition really. The inverse is with respect to this composition. Now, similarly, suppose you take the trigonometric functions, then look at sin x for example. So, sin x has the domain as the whole of real numbers and its range is -1 to 1, but it is periodic. So, if you look at sin x, it will be periodic. So, that is, it goes something like this. So, the pattern is repeated, and then you see that minus pi by 2 to pi by 2, if you start with this, you achieve your -1 to 1 values. So, that means from this place, the restriction of sin x to this domain minus pi by 2 to pi by 2, this one gives you a 1 1 on 2 function from minus pi by 2 to pi by 2 to -1 to 1. So, you can define its inverse, right. So, since its domain is minus pi by 2 and its range is -1 to 1, this is brought by sin x. Then you can think of its inverse, which is -1 1 to minus pi by 2 to pi by 2. That is your sin inverse x. Okay. So, that is what we say, that sin inverse x is a function from -1 1 to minus pi by 2 to pi by 2. So, how does it act? If you take y here, then it goes to sin inverse y here in such a way that if this is your x, this becomes sin x, y becomes sin x. So, that is what we say, that sin inverse x is that number y in minus pi by 2 pi by 2 for which sin y becomes equal to x. So, that when you take sin of sin inverse or sin inverse of sin, they become identity functions on their respective domains. But remember that sin -1, which we write as a superscript x, is not same as sin x to the power -1. Though we write say 3 to the power -1 equal to 1 by 3, and it is looking the same way, something like sin inverse is -1, but it is different from sin x to the power -1. Sin x to the power -1 is cosec x, but sin inverse x is not cosecant x, it is different. It is inverse of sin x with respect to composition. Similarly, we can define cos inverse x, tan inverse x, secant inverse x and cosec inverse x.